So if I take the derivative of that function, that will be just x squared minus 5x plus 4. Okay, now setting that derivative equal to 0, well, it's a quadratic that we can factor. X minus 1, x minus 4, which means we have x equals 1 and 4. So we have two critical points of 1 and 4. Now we're not getting a closed interval here, so those are the only values we need to check. So let's go ahead and make a chart, x, f of x. Right, so the value of f at 1. Right, so I'm going to plug that back into the original function. All right, so 1/3 times 1 cubed minus 5/2 times 1 squared plus 4 times 1 is 11/16, or 11/6. All right, now if we evaluate that function at 4, 1/3 x cubed minus 5/2 x squared plus 4x. All right. That is -8/3. So we have a local maximum of 11/6 at x equals 1, and a local minimum of -8/3 at x equals 4. Now, if we sketch this graph, our graph looks something like this. It's a cubic. So we definitely will have a maximum and a minimum. So that graph verifies what we just see there. All right, number 8, f prime of x. The derivative of that would be 3x squared minus 1. With our chain rule of squared times 2x. Now, setting that equal to 0, we can see that we're going to have x equals plus or minus 1 from that term there, and x equals 0. So we have 3 critical points. The derivative is never undefined. All right, so let's go ahead and plug these values into a table. So x, f of x. So we're plugging these into the original function. All right, we'll evaluate this at -1, 0, and 1. So at -1, we have a value of 0. At 0, we have a value of -1. And at 1, we have a value of 0. Okay. All right, so we know we have a local maximum of 0 at x equals -1 and 1. Okay. Now, that may seem strange because we have 2 values there. So this may depend on what our function looks like, because if it increases past those 2 points, because like the last one we had a cubic, so it appeared to be lower on one side than the other. Okay, so let's go ahead and continue writing this. So a local minimum of -1 at x equals 0. All right, now what this function looks like is something like this, which I knew in advance. Okay, so I've obviously got a minimum at 0, that was this right here, So this actually is an absolute minimum. It's actually an absolute minimum. However, these 2 points at -1 and 1, neither one of those are actually a maximum. They are critical points, however. So that is worth noting. That's why we want to check these with our graph. Now we are going to see something called the first derivative and the second derivative test in a couple of sections that will help us do this a little more precisely. All right, number 9, we will find f prime of x. So this will be low d high. So 1 plus x squared times 4 minus high d low over low low 1 plus x squared squared. All right, which will simplify to -4x squared plus 4 over 1 plus x squared squared. So we want to look for where the derivative is 0. And the derivative is 0 whenever the numerator is 0. So -4x squared plus 4, which means x equals plus or minus 1. And the denominator will never be 0 because we have 1 plus x squared. So we never have f prime of c being undefined. But we have critical points at -1 and 1. So let's plug those values in. All right, so 4x divided by, into the original function, 1 plus x squared. Okay. So plugging in -1, we get a value of -2. And plugging in a value of +1, we get a value of +2. So at first glance, we have a local max of 2 at x equals 1, and a local minimum of -2 at x equals -1. Right, now looking at the graph of this function, a sketch of this, we have something that looks like this. So at the ends, positive and minus infinity, it's approaching 0. So we have a minimum here and a maximum here. And in fact, these are absolute min and max. And there we have it. Alright, next we have this one over a closed bounded interval from 1 to 3, so our endpoints will be valuable to us because, as we said previously, wherever we have a critical point, that is where f prime is 0 or f prime is undefined, as well as our endpoints. So if we have endpoints, we want to check those. Alright, so f prime of x equals -2x plus 3. So setting that equal to 0, it'll never be undefined, but setting it equal to 0, we get x equals 3 over 2. So we want to evaluate each of these. All right, -x squared plus 3x minus 2. All right, so evaluating at the point 1, 3 over 2, and 3 are endpoints. So evaluating at 1, we have a value of 0. 3 over 2, we have 1/4. And at 3, we have a value of -2. So it appears we have a local max of 0 at x equals 1. Or these are our potentials, I should say. A local max of 1/4 at x equals 3 over 2. And a local minimum of -2 at x equals 3. Alright, so our graph, since we do know what the endpoints look like, at a value of 1, it is 0. This is quadratic, so at 3 over 2, we have a positive value there where the slope is 0. And at the value of 3, we have negative 2. So we have a graph that looks like this. All right, so it looks like we have an absolute maximum for that second one. Absolute maximum there at 3 over 2. An absolute minimum at x equals 3. And the first one was in fact local. All right, now for our last equation, we will find f prime of x equals 2x minus 2x to the negative 1/3, which is 2x minus 2 over x to the 1/3. Now, let's go ahead and make a common denominator. 2x to the 4/3 minus 2 over x to the 1/3. Now, setting that equal to 0, a little bit of algebra tells us we have values at plus or minus 1, where it's going to be 0, and it's going to be undefined. The slope is at x equals 0. So let's go ahead and evaluate each of those. Okay, good. All right, if we evaluate that at negative 1, negative 1 is actually outside of our interval, so we don't need to test that value. So we've got our endpoints of 0 and 2, and then we have the critical point of 1 that we need to work with. So at 0, the function is 0. At x equals 1, the function is negative 2. And x equals 2, we get negative 0.762. And it continues. All right, so it appears that we have a local, let's go ahead and call it a max until we see otherwise, maximum of 0 at x equals 0, a local minimum of negative 2 at x equals 1, and a local minimum of negative 0.762 at x equals 2. All right, now that graph, again, based on those endpoints, we can say it is at 0, 0, 1 it is negative 2, and then at the endpoint 2 it is somewhere here. So it looks something like that function. So we can verify that we have an absolute max at x equals 0, a local max, so it actually looks like at x equals 2, this is a local maximum, okay, and we have an absolute minimum at 1. Okay, so remember, we want to set the function, the derivative equal to 0, to find our critical points, and that's where it's 0 or undefined, and of course our endpoints. All right, that brings us to the end of this section.